All right, cool. So we have these exponential growth and decay type problems, and what they usually start with is they start by saying the rate of change of something. Okay, so rate of change of something, that is d. This is the rate of change of some quantity p, so this would be dp dt. Right, that's a rate of change, right? And then when we're talking about, then they say, is directly proportional to something else. Okay? Do you guys remember in Algebra 1 or Algebra 2 when they talked about directly proportional and inversely proportional, what those equations were? And then there was direct, inverse, and joint. Those were the three, right? Yeah, you did in Algebra 2. There were three variables. Do you remember what directly proportional was? Yeah, it's like y equals, the output equals like k times x, right there, and your center was 0, 0 always, right? The origin was always your center, but then this was like y equals kx. Directly proportional is y equals kx, but since it's directly proportional to p, that's why we write it as the rate of change, this part, the rate of change dp dt is directly proportional to p. That means k equals kp. Okay. So anytime you see directly proportional, it'll be kp. What if it said the rate of change is inversely proportional to p? Then it would be dp dt equals k over p, right? Okay. Usually you don't see that because in exponential growth and decay, it always starts with like this kind of setup, because this is what happens when you separate and integrate that. So if I took dp dt equals kp, and I got all the p's on one side and all the t's on the other, I would have 1 over p dp equals k dt, right? From our separate and integrate section. Okay, now it's separated. Now if I integrate both sides, then the integral of 1 over p is natural log absolute value of p equals k t plus c, right? Yes,
I was just confused still in the first part. Why is it KP and not KP to the double prime? Like,
what do you mean?
because it's DP over DT is equal to KP, and it says it's directly proportional to P with the two apostrophes.
Oh, yeah, that's the end of the
I thought that was like the second derivative.
If Albert didn't say that, I would have never known why you thought it was double prime.
Okay. There we go.
Oh man, we need Albert to decipher. It's like, where is she getting double prime from? Second derivative. Okay, we're all good. Yeah, that's the end of the quotation mark. Maybe I should delete that and put like a colon here. Well, who cares? Okay, we're going to get rid of the natural log, and I'm also going to get rid of the absolute value by simplifying and just saying p equals, and then what happens when I exponentiate the kt plus c? Yeah, I think you all said it. It was very mumbled, but it becomes e to the kt, but then the e to the c part will relabel as a. So
What is the equation for jointly related?
joint is z equals kxy.
I don't think my class ever did that.
You had to have done it. It was on the SOL. I don't know why you really need it, but whatever.
I was sure with Marshall.
Oh, okay. Then I don't know.
Marshall substandard.
I learned it.
Who's your teacher?
I don't, if you want to label that on the side, you can. My teacher was Mrs. Champ.
Well, she's not there.
She's not there anymore. She retired like a couple years ago. Okay, so you can always think that the rate of change is directly proportional, which is dp dt equals kp. Automatically translates into p equals ae to the kt. But sometimes it doesn't say directly proportional to p. Sometimes it says directly proportional to p minus 2, or directly proportional to p squared, or something else. Then you can't go straight to this formula. You're going to have to separate and integrate. I think there's a problem on your homework that's like that, where it says the rate of change is directly proportional to the square root of p. And then if you separated this and this had a square root, then when you brought it over to this side, you wouldn't do natural log to integrate. Yeah. Okay. You guys are just so excited tonight.
Without a clearance.
Yeah, me too. But that's okay. We're less than 2 weeks away. All right, so let's do one. You run over a nail. As air leaks out of your tire, the rate of change of the air pressure inside is directly proportional to that pressure. So this is the rate of change of pressure is directly proportional to that pressure. I don't have to separate and integrate again because it's the formula that we already solved for, so we can just go straight to, oh, that's our first one, write a differential equation. This is our differential equation. Okay, and then, so I know that the initial pressure, whoa, bless you.
Sorry.
That's okay. That's like my dad and Mr. Burkle. They both sneeze really loud. It's 35 pounds per psi, so that's P. And then this is decreasing at a rate of 2.8, so dp dt has to equal negative 2.8, negative 0.28, right? Okay, everybody good with that? All right, now we solve for k. We can plug those in and solve for k. So negative 0.28 equals k times 35. So k equals negative 0.0008. Okay, solve the differential equation. Well, we already know that differential equation solves to P equals AE to the KT. And I know K, so I'm going to plug that in for K. All right, A is always like your initial condition because if T is 0, then A always ends up being like your starting value, right? So if you, at the time your nail was struck, the pressure is 35, we'll plug 35 in for A. And then now we have all the equation to solve C and D. So pressure 10 minutes after it was struck is and don't if K is number, don't round it until the end of solving the problem. So if you need to store that value, you best do it. So I got 32.309. What's my pressure? Pounds per PSI. Why do you abbreviate pounds into LBS? That's the units that it gave us, so that's the units we're sticking with. Yes. I'm listening.
Wait, why did you put 35 in for A? Like, why should that be?
Oh, because that's our initial pressure.
Okay, but why is A initial pressure?
Because if I plug 0 in for T and 35 in for P,
Oh, okay.
We're doing pounds per pound per square inch.
That's what I said.
you know, just go with it. So A has to be 35, right? So it's always 0. Like A is like always your value when T equals 0.
You said that.
Okay. Last problem. The car is safe to drive as long as the pressure is 12 pounds per PSI or greater. So if we set this to 12.
But isn't this just like inches here? So like pounds per square inch.
Times T. And then we solve for T.
Not unit.
But don't simplify your answer. Until the end. Did you get 133.805?
Yeah.
Okay. Minutes? Okay, that's exponential growth. And now it's time for you to do example 2 and 3. And then we'll do logistic growth together. Okay, so you try 2 and 3. All right, so let's see. What did you get for A? Did you get dP dt equals Kp? Okay, so which means that you can automatically go to P equals AE to the KT. And so your formula for part B should have been P equals 4,700 E to the, what was your K? T. And so if your K is negative, it's going to be exponential decay. And if your K is positive, it's exponential growth. What'd you get for C? What'd you say?
Wait, no, that's not what I got.
I got 2,994.
Boy.
They store the value for negative 0.035.
Well, I should.
Some people sorted, some people just did negative 0.035.
Oh, wait, I think it's just that, like, maybe you didn't like
Did you store your variable or did you?
Oh, yeah. I didn't round my variable.
You're right.
How do you store?
No, so you have to store.
You have to store.
I didn't read that that's just like
If you don't store, you're missing something in life.
I don't think it's way 0 plus 1. I think it's 0 plus 1.
It's 0.0375. But anyways,
But if you store, it doesn't matter.
yeah.
Where did he get negative 0.07?
I solved for it.
Yeah, I did it and got negative over 0.5.
I got $2,997.12.
Yeah.
Did you get this?
So are you doing like negative 5
Wait, I thought we were
over
doing 3 decimal.
No, you can't do that, Albert. Because, are you plugging negative 500 over 3 into DPDT? You can't, because DPDT is a instantaneous rate of change, not average. So 500 over 3 is an average rate of change over a certain interval. You have to plug in, shh, guys, I know you're talking math for a lot of this, but just let me explain without having to talk over people. That's how I solve for K. All right. Yeah. So guys, you can't do 500 over 3 for DPDT because DPDT is an instantaneous rate of change. So don't do 500 over 3 because that's your average rate of change over the 3 months. Okay. All right. For D, what'd you get? 36 point. Okay, and then months. And then D, what was its new value? 25.
15,026.8, yeah.
How did no, it's
0.8.
Wait, it's 25. Wait, how did you set up
E?
get that far. Yeah.
You do P equals 4,700 e to the, but use your stored value. Yeah. And negative 31.
Also, can you also do like put set P equal to 4,700 and then do
Yes.
A?
Yeah. Okay, purchase price when it was new was 1,600. How do you explain the difference?
salesman drives it?
Yeah. Car dealership got you.
Would they ask you that question?
Car dealership had your number. They knew you wanted the car. They were like, fine. All right, let's do example 3. Carbon 14 is radioactive and decays at a rate proportional to the amount present, which means dPdt equals Kp, which also means that we can go automatically to the formula. P equals Ae to the Kt, right? And then 10 grams were present originally, so I can plug in 10 for A. And then it says its half-life is 5,730 years. So if its half-life is 5,730, then at t equals 5,730, what will my p equal? Yeah, because it's a half a life, so half of it should be left, right? Now I can solve for k. So 0.5, natural log of 0.5 divided by 5730. Whoa. So there's my k. How much is left after 2,000 years? And guys, on free response, once you label what k is, you don't have to like put that in your exponent because they will know to put that up there. So 10e to the k times 2,000. You get to 7.851 years. Okay? Feel good? Never mind. You know, grams, years. Today's opposite day. But then it's not opposite day. You'll never know. Okay. So on this exponential growth and decay was this like dp dt equals kp. So if you follow this slope field, then it's always exponential growth. If k is bigger than 0, right? And if k is less than 0, it's now exponential decay, right? Yeah? So we have exponential growth and exponential decay. But 90% of the time, things that happen in nature don't just exponentially grow or just exponentially decay, right? At some point in time, there's like, it levels off. Carrying capacity, right? So like, if you're spreading a rumor, it's going to grow exponentially for a little while, but then at some point, after it grows exponentially, then it's going to start leveling off, right? So that's what we call logistic growth. So it models more real life situations than exponential growth does. So this is a new one. So that formula is the same as this one, only what we do is we throw in a limiting factor. So we say, all right, it's directly proportional, but then let's throw in this limiting factor, parentheses, L. I'm going to add a slider. Hold on. Minus y. Okay? So what that does is it limits it. I'll make my L 5. Okay? So if you notice that it grows exponentially, but then it levels off like that. If you look at your slope field, the last slope field we did in the notes, that was in a logistic growth slope field. So the middle part ends up increasing like this and then leveling off, right? What? It's got, we got two horizontal asymptotes. We've got two places where your slope is 0. Okay? because this is the carrying capacity. This is like the most amount of people that will have a disease, or a rumor will spread, or like population of fish in a pond or something like that. Okay. There's important things about this logistic growth. When we get to partial fraction decomposition integration, we'll actually solve for the initial one, but right now we can't solve for it, so we're just going to talk about like special characteristics that the logistic function has. So if it's here, like they'll always give you an initial condition right here. That's going to be your initial condition. And then this is your L, so it's your limiting capacity. This is like another horizontal asymptote. Both this and this are places where your slope equals 0, right? Your first derivative slope equals 0, right? But you have a y value, and you have horizontal asymptotes at like 0 and 5. If your initial condition is up here, then your graph is going to be like this. And if your initial condition is down here, it'll be like this, but like we never really look at those kind of things. So we are growing exponentially and up until here. And if you do the calculations like we did for the slope field before, there's a point here, and it's specifically halfway in between your carrying capacity and your and 0, and that is, what does it look like on the graph? It looks like a point of inflection, right? So this is where the second derivative equals 0. It's also your point of inflection. Okay. And then it's also, more importantly, where you're growing the fastest. So on free responses and stuff, since logistic growths always look exactly the same, if they ever ask you, or if I ask you, hey, where is it growing the fastest? And you know the limiting capacity is 5, you can say it's growing the fastest at 2.5 because it's a logistic growth function and it's always growing the fastest at half of its carrying capacity. Okay. They use this model a lot in economics. So if you major in econ, then they'll use this model a lot. This is how Sam Walton, the guy that invented Walmart, this is like why he started making so much money back in the day, because what he would do is he would analyze the rate at which people were buying things off of like the shelves, and then the minute the rate started to slow, he stopped buying that item, so he had enough item to like have the inventory for everybody else that was going to buy it, but never had too much inventory. So that was like his whole premise of Walmart, was to always have enough for everybody that wanted it, but never have too much. Okay. Let's do some logistic growth then. So the nice thing about logistic growth is it always looks exactly the same. It'll either be in this form, and a lot of times they'll say this is a logistic growth function. It'll either be in this form, dp dt equals kp times L minus P, but sometimes they will do it in this form, where it's basically multiplied together. So if it's in that form, no big deal. Just pull out the P So just pull out the P. And then to find where your limiting capacity is, your limiting capacity is going to be where dp dt equals 0. So there's two locations where that happens. That's where p equals 0 and where 3 minus p over 6,000 equals 0. So what are my two places? If I solve for p, it's at 0 and at 18,000. Okay. So, you know logistics. Anytime you have a logistic, draw a graph of it. I think the last part of this problem tells you to draw a graph, but just do it from the very beginning. So we know we have a horizontal asymptote at 0. And we know we have 1 at 18,000. That's where our slope, our dp dt, equals 0. And these are y values, not x values. So, okay. And then our initial condition, p of 0 equals 4,000, means I can put an initial point at 4,000 here. Okay, so if I drew my solution curve, it would go up through this intersection and then this way. And then my point of inflection, or where I'm growing the fastest, is what? 9,000, because we always said it happens at half of its carrying capacity. So, at 9,000 we have a point of inflection, which is awesome. Now we have everything we need in order to solve the logistic problem. So, what is my limit as t goes to infinity? So on this graph, as t goes to infinity, what y value am I approaching? Okay. What is the range of my solution curve? 0 to 18,000. Let's go 4,000 to 18,000. Because it's range. So it's y values. And because, like, you know, we're not talking about, like, if we're talking about 18,000 is the top, the highest point, then we have to start at 4,000. It's our initial condition. For what values of p is the solution curve increasing? Well, the whole way it's increasing, right? The whole way here. So we're going to say increasing from 4,000 to 18,000. And these are values of p, not values of t. We're always going to work with p values for logistics. For what values of p is the solution curve concave up? So since you know the point of inflection, you should be able to tell me where it's concave up. 4,000 to 9,000.
How would we justify C?
For C, you can just say within 0 and the limiting capacity, a logistic curve is always increasing. Or you could solve it. So there's two ways to justify. You could say dp dt is always greater than 0 on the interval 4,000 to 18,000. But you could also write it like, you could also say logistic curves are always increasing in inside the two horizontal asymptotes. You know, either one is fine because it would be true for no no matter what logistic curve. Okay, we're concave down from 9,000 to 18,000. And if you want to justify your answer by logistics, you could say logistic curves always have a point of inflection at the carrying.
9,000 hard bracket.
You can do it however you want to.
Why does 9,000?
I said you can do it however you want to. So you can have it or you don't have to have it. Okay. Does the solution curve have an inflection point? Yes. At P equals 9,000. You might, it's not at T equals 9,000 because logistics you're always looking at the y-axis, not the x-axis. And then you can use the same reasoning for E as you do for D. And we have already done F. Okay, I'm going to help you sketch the curve to the next two. It's the same function, but your initial condition is different. So this one, you still have asymptotes at 0 and 18,000. But the difference here is your initial condition starts at 10,000. So did your point of inflection already happened before before the curve starts? So this one is just going to be increasing, but it's going to be concave down. So that's what that one's going to look like, because when it hits the point of inflection, it's before t equals 0. And then the last one, you still have two horizontal asymptotes, one at 0 and one at 18,000. But your logistic initial condition is going to start all the way up here at 20,000. Meaning it's going to always be concave up, and it's going to be decreasing towards your asymptote, but never actually touch it. Okay? Your job now is to answer all of the questions for 2 and 3, and then you have the choice to do the homework or the corrections to your test. Those are due today if you want points back. Correct your test. And then that's it for today. All right. Well, logistics all look the same. You just have to know special characteristics about them.